Hi, thanks for joining me. Today I've got a fun problem from the Putnam 2020, and this is problem A3. We have a sequence of numbers where the first term, A1, is 1, and then the n plus 1th term is given by sine of the nth term. So an plus 1 equals sine an for all natural numbers n. We want to know, does the infinite sum, the sum from n equals 1 to infinity of an squared, converge? Okay, so what is this sort of series? It's 1 squared plus sine of 1 squared plus sine of 1 squared, and so on. So quite an interesting series, and we want to know, does this converge or diverge? Okay, so if you're going to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the solution to this problem is that this series diverges. Okay, and I've made a little claim, is that an is a decreasing sequence of positive terms. Firstly, to see that it's decreasing, to see that they're all positive, a1 is clearly positive, it's 1, and sine of 1 is going to be some number between 0 and pi over 2, because sine of any number between 0 and pi over 2 is going to be between 0 and 1, but in particular between 0 and pi over 2. So kind of by induction, each of these terms here are going to be positive, and in particular lie between 0 and 1. And it's clearly decreasing because sine of x is less than x for positive x. So it's a sequence of decreasing positive terms, which kind of suggests that it's going to converge because they're going to go to 0, the terms, but also we're looking at the squares of the term. So when you square something that's going to 0, it's going to go to 0 even faster. So it suggests that it converges, but in fact it doesn't. And it kind of grows a bit, and it's kind of like the harmonic series, because the harmonic series, intuitively, you'd think that it converges because each of the terms are going to 0 relatively quickly. But of course we know that the harmonic series diverges. Okay, and we're going to see that this is actually quite similar to the harmonic series by doing a comparison test. But the first thing I want to do is have a look at Taylor's theorem and look at sine of x. So by Taylor's theorem, sine of x, what we know is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. Oopsie daisy. Okay, but a particular sort of statement of Taylor's theorem says that we can kind of truncate this sum after whatever number of terms we want. So I'm going to do it after the x cubed term. Okay, but what we have to do then is add on kind of like an error term. And this error term is going to be sine to the 4th derivative. So the 4th derivative of sine evaluated at some psi of x. So psi is some number which may depend on x. Okay, divided by 4 factorial times x to the 4. Okay, so if you've not seen this before, basically it just means we can truncate the sum. We just have to add on, remember here there's kind of an invisible 0 times sine, the 4th derivative of sine times x to the 4 over 4 factorial. But yeah, so here we've got to add on the 4th derivative of psi of x, where psi is just some real number which depends on x. Okay, so this thing holds true. Sine of x equals x minus x cubed over 3 factorial plus sine to the 4 of psi of x divided by 4 factorial times x to the 4. But notice that because in this problem we're only considering x to be the sort of, or these an terms, and each of the an terms I've shown is it's decreasing and positive, so each of the an's lie between 0 and 1, then in particular, well, firstly, sine to the 4th derivative, the 4th derivative of sine is just sine, so I can get rid of this. But in particular, each of these psi of x's are going to be between 0 and 1. So psi of x is between 0 and 1. Okay, let me clean up the whiteboard and we'll continue. Okay, so we've just shown that sine of x equals x minus x cubed over 3 factorial plus sine of psi of x over 4 factorial times x to the 4, where psi of x is just some number which depends on x between 0 and 1. Now this doesn't hold in general, but this is only for the x we're kind of considering in this problem, where x is these an's, so some numbers between 0 and 1 anyway. Okay, so we have this thing here, and now I'm going to make a claim. I claim that an is bigger than or equal to 1 over the square root of n. And in fact, before I make that claim, I've already said it, but before I make that claim, I just want to make a little statement about this. Because psi of x is between 0 and 1, that means that sine of psi of x is going to be positive. So this term here, remember x to the 4 is positive, this guy here is going to be positive. So in fact, I can write this thing here is greater than or equal to x minus x cubed over 3 factorial, which is just 6. Okay, so sine of x is in fact bigger than x minus x cubed over 6 for x between 0 and 1. So these an's that we're considering. Now, as I said, my claim is that an is bigger than or equal to 1 over the square root of n. Now notice that this is actually going to solve our problem. This is going to prove that the sum of the squares of an diverges. Well, why? Let's just write it up here. If this is true, then the sum of the squares of an is going to be bigger than or equal to the sum of 1 over root n all squared, but 1 over root n all squared is just 1 over n. And of course, this guy here diverges off to infinity, so by the comparison test, this thing here will also go off to infinity. Okay, so that will solve our problem, but of course we've got to prove this claim first, and the way we're going to do that is by induction. So we're going to prove this by induction. Let's firstly look at the base case. I'm not going to write it out, it's very obvious. A1 is greater than or equal to 1 over the square root of 1, which is 1. So we want to show that A1 is bigger than or equal to 1, but by definition A1 equals 1, so that's perfectly true. Now let's assume that it holds true for some n equals k. So assume that AK is bigger than or equal to 1 over the square root of k for some k. Now what we're going to do is the inductive step. So now we're going to look at AK plus 1. So we want to show that AK plus 1, well, we know that's just sine of AK. We want to show that this guy here is bigger than or equal to 1 over the square root of k plus 1. So this is what we want to show. Let me write it here. Want to show this thing here holds true. But now from our previous statement here, sine of x being bigger than or equal to x minus x cubed over 6, where x is some number between 0 and 1, means that it's to show this inequality here, it suffices to prove that AK minus AK cubed over 6 is bigger than or equal to 1 over the square root of k plus 1. And the reason for this is because if this thing here holds true, then we know that sine of AK is bigger than this or bigger than or equal to this thing here. So in particular, it's going to be bigger than or equal to this thing here, and we'll get this thing here. Okay, but we can actually go one step further, because if we consider the function f of x equals x minus x cubed over 6, if we just differentiate this guy, we can see that this thing here is so the derivative is positive. So that means that f of x is an increasing function in 0, 1. So its derivative is only positive in 0, 1. That's all we're considering for this problem. So it's an increasing function in 0, 1. So that means that in fact I can take this one step further, and because we're assuming that AK is bigger than or equal to 1 over root k, I can make a further sort of it suffices to statement and say that we can actually, it suffices to prove that 1 over the square root of k minus 1 over the square root of k cubed over 6 is greater than or equal to 1 over the square root of k plus 1. So I claim that if we can prove that, then this proves this statement here. Why? Well, this statement here, if this thing here holds true, then because f of x is an increasing function, and we're assuming that this guy here, 1 over the square root of k, is less than or equal to ak, then that means this expression here is going to be less than or equal to this expression here. So if this expression here is less than or equal to this expression here, in other words, another way of saying that is this expression here is bigger than this expression here. So this is bigger than that, which we're going to prove is bigger than that thing there, and that will prove our claim. But of course, we've got to prove this thing here, but this is a bit of algebraic manipulation which requires a few tricks. Let me clear up the whiteboard and we'll prove that. Okay, so what we've shown is that to show that our series diverges, it suffices to prove that this inequality here holds true. The first thing I'm going to do is rewrite this, sort of changing these square roots into index powers. So this is true if and only if, and I'm just rewriting this inequality, 1 over k to the half minus, and then sort of simplifying this, 1 over 6 times k to the 3 over 2 is greater than or equal to 1 over k plus 1 to the half. First thing I'm going to do is times both sides by k to the 3 over 2. So this thing here, when I times it by k to the 3 over 2, I'm just left with k. So this is if and only if k minus 1 over 6 is bigger than k to the 3 over 2 divided by k plus 1, like so. Okay, and now what I'm going to do, to the half. Square both sides now. So this thing squared is going to give me k squared minus, and perhaps one thing we should be careful of is when we square inequalities, we've just got to maintain the inequality sign, we've just got to make sure that both sides are positive, but this side's clearly positive because we're taking sort of k and k plus 1 are positive when looking at their roots, and they're defined to be positive, and k is a natural number here, so this is positive. So there's nothing to worry about with squaring both sides. So if we square this side, k squared minus 1/3 k plus 1 over 36 is bigger than or equal to this side squared, which is just k cubed over k plus 1. And you can guess what I'm going to do next. Multiply both sides by k plus 1. So if I do k squared times k plus 1, that's going to give me a k cubed plus k squared. If I multiply minus 1/3 k times k plus 1, that's going to give me minus 1/3 k squared minus 1/3 k. And then this 1 over 36 is 1 over 36k plus 1 over 36, and that's greater than or equal to k cubed. Okay, and of course I can cancel these k cubes from both sides, and now what I'm left with is a quadratic which I can clean up and then hopefully work out whether it's non-negative or not. Let me clean up the whiteboard and we'll do the final step. Okay, so the final step is to solve this quadratic inequality. The first thing we're going to do is just collect like terms. K squared minus 1/3 k squared gives us a 2/3 k squared minus 1/3 plus a 36. Well, minus 1/3 is the same as minus 12 over 36. So minus 12 plus 1 gives us a minus 11 over 36k, and then plus a 1 over 36. The next obvious thing, multiply both sides by 36. So this thing here is going to give us 12 divided by 30, multiplying by this, 2/3 times 36 is 2 times 12, which is 24. I'm losing my words today. 24k squared minus 11k plus 1 being bigger than or equal to 0. And these are all if and only ifs. Okay, and this thing here very nicely factorizes as 8k minus 1, 3k minus 1. Okay, and then you can just expand this here to check that this thing equals this thing. And very clearly this inequality is true. And the reason for that is because k is a natural number. So 8 times k minus 1 is going to be at least 7. And 3 times k minus 1 is going to be at least 2. And these are positive numbers. Multiplying two positive numbers is going to give you a positive number. So this inequality is true. And if you sort of backtrack, that proves that the sort of it suffices to statement is true. And thus our induction step is true. And therefore we're done with our proof in showing that an is bigger than or equal to 1 over root n. And as I said before, just by doing a comparison test, that tells us that the sum of an squared diverges because the harmonic series diverges. Anyway, I hope you have enjoyed this video. A nice fun Putnam problem for you. Thanks for watching. I'll catch you in the next one. Have a great day.